Larry, it's a pleasure to see you, and especially, at the kickoff of our conference where we're here to talk about transcending digital and really the power of human innovation into this new century that we've entered into. But I think what's burning on my mind, and I think probably on everybody, is can you give us insight into how things are going on in Mars, and particularly with ingenuity and perseverance? I mean, helicopters on Mars, this is a big deal.
Well, sure, Kevin. Things are going well. Things are going pretty much as planned. We, as you know, landed on February 18th with the rover, and it takes a lot to get things going because there's a lot of complexity to the rover, a lot of things that have to be checked out. And so that's the process we've been in with the rover initially, and of course then after we'd done some initial checking, we deployed the helicopter, which is also a very complex maneuver to drop the helicopter on the surface of Mars and drive the rover away, then check the helicopter out. And of course, with any high-tech instrument, we had a couple problems with some of the software on the helicopter where we had some limits that were prohibiting the helicopter for the blades reaching full speed. So we spent a few days working through that and uploaded some changes. And then of course everything has been working great. So for the rover itself, we're also now starting to do science, where we have these instruments that look at the various rocks that are interesting to the scientists and the geologists. We can take remote spectrum analysis of those. We have other instruments that can get very close to the surface and rocks and things like that we're checking out. And then ultimately, the rover itself is about caching samples to bring back to Earth. That is the key mission. It's the first step in the Mars sample return mission. So we just started this week to check out the whole rover arm actually then inserting itself into the caching system where we have to place the samples on the rover. So we did the first test of that this week. But it's a fairly long process before we actually get to taking samples here in the next month or so. Yeah. So that's all going well. And then the helicopter, as you know, it's had 5 flights on the surface of Mars. Each time we extend the height or extend the range. And then we completed 4 flights, which is really our primary test flight system, because this really is a tech demo. It's not required for the mission, but because things have gone so well, we said, well, let's use the helicopter operationally to fly ahead of the rover,
right,
scan ahead, and see what's out there as we prepare to drive the rover south. So that's kind of where we are.
So, but the process of innovation is really miraculous here, because all from the Viking missions on, I mean, in order to get to a point where you can actually fly a helicopter on a foreign body, you have to be able to simulate that environment on Earth. Right. You have to know exactly what the environment is going to be, and I think what people may not realize is there are many discoveries along the way.
There really are, because you think, oh, okay, I can just take a drone that's on Earth, launch it to Mars, and fly it. But the reality is, the Mars atmosphere is 1% of the Earth. Mm-hmm. So you're talking 80 miles high or 100, I don't know exactly the altitude, but it's pretty high up to simulate that atmosphere. So there's virtually no air to fly in. So we had to come up with, counter-rotating blades on the helicopter that rotated between 2,000 and 3,000 RPMs just to get enough lift. We had to be very innovative in terms of just the payload. We have a couple of cameras and really kind of a total 4-pound package. That's it.
And you have to pack a lot in there, right?
Pack a lot in there, and then as you said, then we had to simulate, can this thing even work? Right. So we have a big 25-foot high chamber that we can evacuate and put the right temperature in. So we created the atmosphere of Mars in that chamber, put the helicopter in it, and then actually flew it in that chamber to show that, yeah, this thing will work in 1% Earth atmosphere.
Yeah. See, I mean, with all the technology innovation, there's some real social implications, I think, and human implications that we're always struggling with in this conference and body, right? We meet with all the executives here. We talk about the challenges of innovation, but we also talk about the implications on humanity. Mm-hmm. And the politicization of space. I want to get into that a little bit, because it means something when we are there as JPL, NASA. Maybe there's a race to Mars now with China and other nations. Obviously, we have our perspective on not making this into a competitive space, but the reality is we have bilateral relations with some countries. We have Space Force, which is a very unilateral position that we're taking, where we're going to protect our assets in space. And then we have a multilateral mission like Artemis, where we're focused on the right things to do, and ISS, of course. How does all of this play together and JPL's role? I know it's a big question, but if you can sort of dive into the differences in the challenges as in your role, and I think that's what's special about the discussion today is you come to us like a chief operating officer who can come in and say, we have a lot of challenges that we have to deal with to be able to do the science.
Yeah. I mean, ultimately, as you said, JPL's about doing science, right?
Yeah.
For the benefit of humanity, not just for NASA, not just for the U.S., but really for the benefit of humanity. And in that regard, we do partner. I mean, partnerships are extremely important to NASA and to JPL in terms of the missions we have. We partner on a host of Earth science missions with the French Space Agency, the German Space Agency, ESA, the European Space Agency, the Indian Space Research Organization. So we have a host of bilateral and multilateral partnerships. Japan, Canada, they all contribute. So I think those are extremely important, that bilateral, multilateral nature of the business. But then you kind of mentioned the competition component. Frankly, I think there is competition with primarily China, right? We see that in all aspects of the relationship of the U.S. and China, right? It's not just space. So, and frankly, we NASA, we JPL, we have been leaders in space since the beginning, and we kind of like it there, and we want to continue to be leaders in space exploration and space technology. But remember, NASA's role and job is we're a civil organization, space for peaceful purposes. Doesn't mean that we're not going to go out there and continue to compete, if you will, and bring the best technology forward that we can.
And your role in private industry, I think, is critical here as well, because private industry is playing a role that we've never seen before.
Yes.
And a leading role. And how does that come into play? Because with Caltech and JPL, as you said, your mission is pure.
Yeah. Well, first of all, I mean, we partner with private industry all the time.
Yeah.
JPL doesn't. I mean, the rovers, we do a lot building those things there, but we're partnering with multiple industries across the United States and the world to deliver components, right? Our latest, before Perseverance landed, we had the InSight Mars lander a couple years ago.
That's right.
2018. And that was a strong partnership with Lockheed Martin because they built the lander. They did that with Viking back, decades ago. So we've partnered with Lockheed in that arena for many, many years. So the forte of JPL, I think, is more the science instruments and then also putting these complex systems together. So we partner with industry across almost all of our missions in one degree or another. And then you kind of have the new space world, which is the SpaceX's and the Blue Origins. And hey, SpaceX's, the Falcon 9 has launched many of our missions. Access to space is one of the largest prohibitors to really opening space up to humanity, the cost.
Yeah.
And all these new entrants, we applaud them because they're lowering the cost of access to space, and that's a good
that means
thing.
more science and more discovery.
Yeah, more science, more capability. We can put more things up there. Technology is leading us to smaller and smaller instruments, so we can now, create instruments on a small sat or CubeSat that we wouldn't have thought of 10 years ago. A great example that we have is something called Sunrise, which is really 6 CubeSats that are going to fly in formation looking at the sun with really a low-frequency radio receiver that will allow us to detect what's called coronal mass ejections from the sun, which if they hit the Earth, it's a big problem. If we get a blast of coronal mass ejection, it can take down power lines and all sorts of things. And so this is an early
and
warning.
satellites.
And harm satellites. This is an early warning system where we detect the low-frequency radio wave before the coronal mass ejection gets to us. But you can only do that from space. You can't do it from the Earth.
Yeah.
So CubeSats, small instruments, flying in formation, all brand new stuff that we couldn't have done 10 years ago.
And the interesting thing about it is this is very much, I remember from 15 years ago, part of JPL's focus, which is we're going to focus on small unmanned robots, basically,
Mm-hmm.
right? And be able to run more missions and
Mm-hmm.
collect more data.
Mm-hmm.
And of course, during that time, sensor technologies improved.
Absolutely.
We're able to collect
Absolutely.
exabytes of information.
Right.
And that kind of gets me into the next major pillar of subject matter is deep learning. We're collecting so much data,
Mm-hmm.
and JPL's connecting so much data, and you're cross-referencing it against private industry, as you said, other countries as well. How are we going to deal with that? What's coming? What's the science that's going to help us understand how to analyze all this information?
Well, first to your first part, I mean, yeah, the data, is, as we all know, is just growing exponentially. I talked about the partnership with India, which is our NASA ISRO synthetic aperture radar satellite, which we're actually building right now at JPL and in India. Up to 70 to 80 terabytes of data per day coming down. How do you manage that? How do you do something with that? So it does require a lot of new thinking, but we've been thinking about this for a while because we've been creating a lot of data for a while. So we have things, even flying on the space station now, we're using machine learning and AI to, as we look at the Earth with this particular instrument, clouds are a problem. And so this machine, the ML and the AI are determining, well, is this a cloud or not? Should I look here or not? Can I predict ahead or not based on what I know from the past? And it makes us much more efficient. So we're applying, there's tons of data at Mars. We've applied some AI and ML learning techniques to find new craters on Mars so we know the most recent meteorites that have hit. The human can't do that.
Yeah.
And you've got to train the machine to do that. And it's been very effective. We've written papers on that in the last couple of years that show that we can apply this technology to this tons of data and help us glean out information and inferences that we wouldn't have had before.
And I think it's exciting because when we look at these very public displays of success, with Perseverance and all the rovers, we really look at Mars differently. And the title of this session is From Earth to Mars, and
right.
And it's a bit, I guess it's a bit exciting to think about the idea of human beings going there. But we're really setting the groundwork, right, for man to go, women to go, and maybe even to not just visit but to stay.
Right.
Is that in our cards?
Absolutely. I mean, if you look at the NASA strategy or strategic plan, I mean, it is Moon to Mars. It's kind of do your understanding, your learning, your testing as we go to the moon in the mid-20s. But you start to apply that to now, how can I take humans to Mars? And our job at JPL, frankly, has in many ways been not only to do the science, but do a precursor for the humans. So if you go back to the Apollo days in the 60s, we built and landed the surveyor missions that went to the moon and landed on the moon and examined the moon because we frankly didn't know a lot about the moon at the time. How deep is the dust? Will the astronauts be walking in 2 feet of dust or not? How do we plan for that? So, and it's the same with Mars. We send those precursor missions to really understand Mars. So in preparation for humans, ideally in the 30s, for humans to go there under the NASA strategy.
So that's within our lifetime.
Yes.
Now, this is a bit of a funny question. We look at Elon Musk, and he's very serious about colonizing Mars, but for a very different reason. Of course, I think he's interested in the science, but he sees it as an insurance policy for humanity. Maybe because we haven't been so kind to our own planet. And
Right.
And how do you see that? Because obviously we're learning so much from Mars from an application standpoint that can help us with sustainable development here. What's your perspective, maybe personal and also JPL, about the reasons to go?
Yeah. Well, personal and JPL, I guess, but, part of it, I think, is just our ethos as a human. We want to explore. We want to learn. I think that's in all of us. And so as we have the ability to go out further and further, we explore and we learn. That's what draws us to Mars because it's the most Earth-like planet in our solar system. Plus, as we've talked about earlier, I mean, it was like the Earth at one time. So, we've proven with our rovers that there was water there was flowing water, there were seas. They lasted millions, maybe billions of years. There would have been the opportunity for life to grow there potentially. So that's what makes it very interesting. Part of it is the science of understanding what happened to Mars and then how does that apply to the Earth? And then the science of understanding of once we get there, how do we live there? And those are questions that we are hoping to answer in preparation for humans to go to Mars.
Yeah. I probably am more of a realist. I think that the reasons to go there are very practical reasons to go there. What I love about JPL's mission is it's a science-based mission.
Mm-hmm.
When I think about humans there, I immediately think about the competitive nature of humans. What's the first settlement going to look like? Is it going to be like an extension of Caltech with a bunch of researchers? And is that going to be the social political construct? Or is it going to be, more of a political state? What do you see it as?
Well, I think there's two paths. One is kind of the Elon Musk path, really, where he wants to go and just colonize. So let's go and live there as a community, which means in my mind you have a variety of different people doing different things. I think for NASA it is about the science and the research and a sustainable community. So we've talked about, probably kind of, if you think about Antarctica, when we went to Antarctica first, it was like, go explore it, spend a little bit of time there, come back. It's a very harsh environment, very hard environment. Now let's go explore it, let's figure out how to stay there for a little while. And now we pretty much have permanent presence in Antarctica. So I think Mars would be kind of the same way. We go first there, we land, we do maybe, who knows, a month on the ground, whatever it is, then we come back. But then you start building the capability to stay longer and longer, and ultimately over time you have the ability to just harvest the resources there and live there, should you choose to do that.
One of the key legs to innovation, I think, is having access to broadband. This has become, we've seen during this pandemic, work would have been impossible. If the pandemic happened 30 years ago, would we be able to come out of it the way that we have? Businesses have continued, science has continued, research has continued. We obviously have to establish, I imagine, that whole infrastructure before we can even think of traveling to these faraway places, on the moon and on Mars. Can you talk a little bit about what that plan is?
In terms of in those locations?
Yeah. Do we need a broadband kind of infrastructure setup? Right?
Well,
there's a whole communication.
Yeah, I think the answer is yes. Because we're already talking about the lunar comm system, if you will, as we send astronauts there under the Artemis program. And so that's already in discussion at NASA and JPL and other NASA centers to what kind of orbital high bandwidth capacity do we need, and so we're already thinking of designs for that. So the moon, I think, is already in play. And then you think about Mars a little further out, but again, we've had high bandwidth communication satellites around Mars for decades. And that's what allows, because the rover doesn't communicate directly with the Earth. It's UHF up to our comm relays and then back to the Earth.
Right.
And that gives us the high data rate. But we also recognize we're going to need more. So, for example, we're building something called deep space optical comm, which is a laser comm system, which we're putting as a demonstration on our next mission out to the asteroid belt. So we're literally going to fly this thing past Mars all the way out to the asteroid belt and demonstrate laser comm back to the Earth.
Interesting. So that's a totally new type of communication that I've not heard of before, but it's a laser-based communication system.
We've demonstrated it around the Earth. We've had experiments on the ISS that have done laser comm back to the Earth, and even from the moon. But for deep space, that's a new technology because it's a whole different.
So it's a light speed-based technology.
Oh,
so
absolutely.
It's a lot faster.
Oh, yeah, it's laser. Yeah, faster and higher bandwidth.
Interesting.
Yeah.
So, as we build this infrastructure, as we build it, we're not just building the infrastructure to be able to conduct more science. We're also building the infrastructure for more discovery and exploration. What happens back at home? How do you see JPL's mission in advancing sustainable development, and how can you give us some examples of technologies that we've used or developed in this pure science that are benefiting us here?
Yeah. Well, again, autonomy is a big buzzword right now, right? And if you think about how we've had to operate on other planets and way out there, we've always had to build some degree of autonomy into our systems, and we're building more and more. Like Perseverance now has a great autonomous driving capability. So it can,
Well, it has to, doesn't it? Not to interrupt, but because there's so much lag between the time you can give an instruction, right?
If you recall, we have the uplink to the ComSat. That only happens a couple times a day or maybe once a day. So we literally have to get all the data down, build the plan, say now go drive here, and then send up the plan, and then the rover has to execute it, right, without us seeing it. So yeah, but we've also built in that, okay, just drive to point C, and if you see an obstacle, go around it or stop, and that's in the software. So we're doing a lot more of that, so we're more efficient with our driving. So autonomy is one area. I think we talked earlier about just the miniaturization of instrumentation and what that means for our ability to understand our environment around us, whether that's from space or in the air or on the ground. I mean, I'll go back many, many years. Every cell phone camera is based on JPL technology, because we had to build the first digital camera to go out to Jupiter with our Jupiter mission, because the analog camera was too heavy, too big, and took too much power. So
Amazing.
JPL developed the first digital camera that forms the basis of every cell phone camera.
And that's a very practical application right here at Earth. You actually don't need to give any other examples, because we all have a piece of JPL
but there's a host
in
of,
our pocket.
there's a host of just, whether it's, advanced 3D printing. There's a lot of 3D printed stuff on the Perseverance rover on some of the instruments.
Yeah.
And we had a briefing this morning at JPL about what these advanced materials and advanced manufacturing techniques. You can build these incredible structures that you couldn't hog out of aluminum,
Right.
But you can 3D print these things, and they're much lighter, much more efficient, and give you different capabilities that you never thought of.
And we'll need to do that in the moon, and on the moon, I presume, and be able to use materials from there, I presume, to build.
Yeah.
So we talked earlier about Space Force, and I think it's intriguing to people, because we have this concept of science fiction and Star Wars and whatnot.
Yeah.
And I think that kind of excites the mind. But Space Force has a real practical purpose. I mean, it's the support and defense of U.S. assets, and also our partners' assets. Can you talk a little bit about that role and how it's going to play into this larger discovery focus?
Well, I spent 35 years in the precursor to the Space Force, if you will, Space Command. So, you've got it right. I mean, there is competition, right? There are threats in terms of to our space assets, and so Space Force is focused on ensuring that the U.S. has the capability to operate freely in space and protect their assets. That is kind of what the Department of Defense is all about, right? Defense.
Yeah.
And so, that is their role day in and day out. Number one, understanding what's there. That's the whole space surveillance, as we used to call it. Space surveillance, situational awareness, whatever you want to call it. And then understanding what's happening in space. It's a lot different than on the ground, where you can get eyes on very easily. But understanding the environment and reacting to threats and protecting our systems, that's kind of the message for Space Force.
Yeah. It's it actually has a real practical purpose. I mean, and I can only imagine everywhere that we've traveled on Earth, right? We have normal human problems. People get into trouble. People need security, and I imagine all of those things will continue in this new environment. Larry, as we make our way back to Earth, I'm just intrigued by all this opportunity that we're seeing in space exploration. But you're doing a lot close to home as well, and the technology that we're using on Mars and in space exploration, you're also utilizing here to create a healthier Earth and to better understand Earth science. Can you talk a little bit about that?
Sure. I mean, when it comes to Earth science and Mars science or whatever, much of it is just about the instruments. What do we measure? How do we measure? And I think NASA and JPL are at the forefront of developing these incredible instruments that can measure things to a very fine degree. So we have a host of spacecraft in orbit today around the Earth that are looking at things. A great example is we have called a soil moisture active passive spacecraft. It literally measures soil moisture around the globe. And believe it or not, the amount of soil moisture in the ground is an extremely important component of the water cycle. and how that water cycle operates. And so
affecting drought and
exactly right.
crop patterns.
Living here in California, and what's the rain season going to be, the drought season. So, scientists are about building models which can again predict what will happen to our earth and to our land and to the weather.
Right.
And so the more data we put in, the better those models are, and the better our understanding is, and then the better we can react to potential problems.
So policy is shifting now into the Biden administration. We're focusing back on the Paris Accords and focusing back on environmental investments. How is that changing some of the research that you're planning in your research agenda at JPL?
I don't know that it's, we've always been focused on earth science. There's a process called the Decadal Survey for Earth Science, which the National Science Foundation does, National Economy Sciences does, excuse me. And they kind of lay out, here are the priorities for earth science for the next decade.
Right.
So, and that's been done 2 or 3 years ago. They've laid out the priorities. What I see now is that, we will probably be accelerating the development of those systems per the Decadal Survey priorities to really continue to help better understand our planet. So we're kind of creating something called the Earth System Observatory, which is looking at all these different systems that can measure all these different things. It's water, it's carbon dioxide production, it's methane, it's a whole host of things, ocean circulation, ocean height. But those all have to operate in a system, and I see that we will be able to move forward in an integrated fashion to execute those missions in the future, and that's where we're headed.
And that's also interrelated, right? I mean, as going back to your earlier comments, we have to share that data with other countries. They share data with us. We're all living on the same planet. There's no boundaries.
Right.
And I think that's the big, realization too with space exploration, is you realize that we're all on spaceship Earth. What's the innovation cycle like? I mean, we've talked about all this great innovation in Caltech and JPL, and how do you work? How do you keep people focused, or they just naturally come all charged up, ready to go?
Well, I think number one, they are naturally charged. I mean, that's the kind of people you want to hire, right?
Right.
But number two, you have to have the processes in place that harness that energy in an appropriate manner. And I don't think this isn't necessarily rocket science, but I think we do it pretty well in terms of, we give our scientists a broad range of freedom to come up with ideas. And then we have a process that says, now we're going to test those ideas. We have a whole, I was explaining earlier, we have something called left field. It's a room called left field. And we say, okay, we're going to go out into left field and come up with some left field ideas. And literally we bring in different experts and different people, and we're just brainstorming sticky notes, but we have a whole team that knows how to do that well. And then the next phase is
there's actually a science. You got to collect data. You can't just be out there dreaming. You
right.
have to. There's a process.
Ultimately, you got to funnel it down, right? And the cool thing is, the way we think about it is, okay, now we've got this idea. It's funneled down. Can we really do this? Then we have another process where we literally bring in the engineers and the scientists together. Then we put them in a big room with all their design systems and everything, and they spend maybe a week saying, can I design something that meets the requirements you have from a science perspective? Is it feasible?
Right.
Then you come out of that and say, yeah, it is. Now let's go into a real design. So it's a pretty good process, and we do this, tens of times, 50, 80 times a year, and we even have different customers that come in and utilize this capability. But you need a process to harness that energy.
That's interesting. Yeah, you have because you're teaching also how to innovate.
Right.
So, final question.
Sure.
This has been such a terrific discussion because you're a philosopher, clearly. You're a social scientist, clearly. You're a general. You have to be a sort of Renaissance person, scientist, all together. What's your vision of why you do? What motivates you, and what do you think is coming?
Yeah, that's a big question. I think what motivates me, or maybe all of us, is just the excitement of learning new things, discovering new things, and tackling hard problems. I mean, I think that motivates most of us. And so I think certainly at JPL, certainly at NASA, that's the motivation. This is a problem. This is a question. We don't know the answer. We don't know how to do it. But darn it, we're going to figure it out. And and we're coming together and working as a team, and that motivates you, and that certainly excites me. And you've talked about going from 10x to 100x and those kind of things. For me personally, motivating, how do I keep our industry and certainly NASA and JPL on that leading edge, whether it's data, whether it's machine learning, whether it's AI, whether it's new instruments, whether it's new problems. Thinking about how do we stay ahead of that game, that's a big challenge, but it's also invigorating and exciting. And the vision is we need to stay out there. We need to stay on that leading edge. We have to take risk, just like with the helicopter. That's risky business, frankly. You just think it's flying underneath the rover. You got to cover it up, but this thing has to deploy down successfully. It's got to land on the ground successfully. The rover has to drive off without destroying it. A lot of risks there, but you manage them and you go forward. But you got to be able to take risks as well.
Larry, thank you so much for joining
Sure.
us.
My pleasure.
I'll remember what you were saying about risk, because if we're not willing to make that investment, there's no opportunity ahead of us.
Exactly right.
So, thank you so much.
Thank you, Kevin. It was my pleasure to be here, and thank you very much.